All right, this is the first lesson that we're going to talk about in statistics. This is called the counting principle, and the counting principle basically has to do with stuff we do every day. You just don't realize that you do it. And you may not want to do this, but it's always a possibility to count things when you're doing them. And so, for example, my outfit today. I'm wearing the orange tie, I got the blue shirt, I've got the blue pants on. When I go to my closet, I have a certain number of possibilities. I have however many neckties. I have 10 neckties, I have 20 shirts, I've got 10 pairs of pants. How many possibilities of outfits are there? That's the real question that we're going to be answering using the counting principle. So this is section 11.1 that we're going to be going through today with the counting principle. Make sure you're taking notes on this, and you can take the quiz afterwards online. So here we go, counting principle. All of these studying of the combinations are called combinatorics. Combination. You can almost see the whole word in there. Combinations is the study of counting the outcomes of some task. So if that task is going to the grocery store, how many possible sandwich types can you make using different kinds of bread, different kinds of meat, different kinds of toppings, things like that. Pizza is the same way. Choosing outfits is the same way. All of these things are just different ways of saying how many ways are there to pick. And as you can see here, I have two examples of flipping a coin or rolling a dice. Okay? All of them have to do with the possibilities, and that's exactly what we're studying here. How many possible outcomes are there? We're going to go through some systematic ways to do it and some shortcut ways here during this lesson. Example 1. What are the possible outcomes for pulling one letter from the word Tennessee? Well, as you can see, I have a T. That's one possibility. So the possibilities that I could have, and this is going to be set notation, so I could have a T. Well, what else could I have? I could have an E, but that also eliminates this E, and this E. So E is also a possibility. What's another possibility? Well, an N is a possibility, but that eliminates that N. And so we're not saying how many possible letters are there. We're saying how many possible distinct letters. How many possible letters that are different. Okay? So we've got the N, and another choice is S. So these are our possibilities, T, E, N, and S. Not really that difficult, okay? And so those are the different possible outcomes. It would be like saying, am I wearing a green tie, a blue tie, a red tie, a yellow tie, okay? All of these are known as experiments. An experiment is an activity with an observable outcome. So in science, you might do an experiment to say, what happens when you mix pure sodium and water? Or what happens when you mix magnesium and sulfur? What happens when you do that? So you do it and you observe the outcome. The sample space is the set of all the possible outcomes. What happens when we do that? Okay, that's the possible outcomes. Okay, and so we record those. So for example, these are going to be the experiments. And these are the outcomes. So what could possibly happen when you experiment with flipping a coin? You could get a heads, you could get a tails. What about a dice roll? You could get a 1, 2, 3, 4, 5, or 6. Okay? Statistics is a lot about keeping track of things that are happening, and that's what we're doing here. We're keeping track of what's going on. Okay? And so when you see a die, for example, like this big green one here, you know it has 6 sides, and so you can easily observe that. We're going to come up with some easy ways that we can count some things like this. Okay, so that's experiments in a nutshell. Let's list the outcomes. Given this sample set, okay, this is our sample space. Sample space. The set of outcomes for the even numbers would look something like this. Out of this whole set, what would be the outcomes that are even numbers? Well, it would be 2, 4, 6, 8, 10, 12, 14, 16, 18, or 20. That's all of the possible outcomes that could happen that would be even from this sample space. Okay? If you want to try B and C on your own, B is a number that is divisible by 5. I'm going to keep rolling through for B and C. If you want to pause and try these, you can probably already do them on your own. Okay? Numbers divisible by 5. Well, 5, 10, 15, or 20. Prime numbers, a little bit trickier. Got to know the nature of a prime number. We'd say things like 2 or 3 or 5, 7, 11, 13, 17, or 19. Okay? It's picking things out of a group of things, guys. That's all it is. That's all it really is. So far, the counting principle just involves us talking about the possibilities. And that's half the battle, figuring out what's even possible before we figure out what we're going to do. Okay? So that's the first part. Now, experiments can come in two types. A single stage, where you pick one thing from a group, or a multi-stage where you have 2 or more stages. For example, you might say, I do this, then I do this. Or pick a letter and then pick another letter. Okay? And so it requires systematic documentation because you have to keep track of what happened first, or what happened second, etc. Okay? Statistics is about keeping track of the things that are going on. And so that's what we're doing here. We're systematically documenting what is happening. Okay? So you're going to need to learn how to use charts. You're going to need to learn how to use graphs, things like that. Okay? Let's look at an example of a single stage or multi-stage experiment. We're going to roll 2 die. Okay? I've got one here and my other one here. But let's assume that one of them is red. Okay? And so, just for example, I'm going to roll them on my desk here. Okay? Here's what came up. Just by chance, 1 and 1 came up. Well, that's one possible outcome. Well, if we start to think about the types of outcomes, we could have, what about 1 and 3? Or 1 and 6? Or 1 and 4? And so, if I move the other one, I could have 3 and 3, or 3 and 1, or 3 and 4. You have to document them systematically. So here's how we're going to do this. This chart up here, we're going to use one column or one row for just the green possibilities. So I could roll 1, I could roll 2, I could roll 3, I could roll 4, I could roll a 5, or I could roll a 6. Okay? In the red possibilities, I could roll a 1. Oops, meant to pick red there. Let's do it like this. Sorry, guys. Let's do it like this. I'm going to move it over 1. 1, 2, 3. Trying to keep it true to the die, you know, how they have them written. You can go ahead and use the number parts if you want. That'd be fine. I'm actually going to do that when I fill in this chart. Those are our choices for the green and the red. We have 1, 2, 3, 4, 5, 6. Interesting to note here. 1 dot on a die or on a dice is called a pip. Okay? It's called a pip. So this would be saying that this has 1 pip of green and 1 pip on the red. So here's the possibilities that can happen. So we'll have 2 numbers. And in this first row, all of the reds are going to be 1s. But look at what happens. We're going to have a 1 and a 1 rolled. Here we're going to have a 1 and a 2 rolled, a 1 and a 3 rolled, a 1 and a 4 rolled, a 1 and a 5 rolled, a 1 and a 6 rolled. Okay? And so if you fill in this whole chart and we go down, this is going to be a 2 and a 1. And so all the ones in this row are going to be green ones because you roll a 1 on the green die. Okay? If we take this chart to its logical end, okay, I'm going to fast forward to the next part of this chart. We have a systematic list of all the possibilities. Well, look here, guys. If we have 6 possible ways to roll on the green, and we have 6 possible ways to roll on the red, we're going to have a chart here that looks something like this. Okay? A 1 and a 1, a 1 and a 2, 1 and a 3, 1 and a 4, etc., etc. If we go down, we have 1 and 1, 2 and 1, 3 and 1. Okay, so this is the chart. How many possible outcomes are there? There's 36 possible outcomes. Well, what does that mean for us? Now we can start to use this observable outcome, because look what happens. How many ways are there to show 7 pips showing? Well, if we have this giant chart, where do we see a 7? Oh, 1 and a 6, there's 1. There's 1. There's 1, 4 and 3, 3 and 4, 5 and 2, 6 and 1. Are there any other possibilities? No, just this row. So there's 6 ways to show that. What about for 11 pips showing? Well, I'm thinking 6 and 5, so I've got a 6 and a 5 here, and I've got a 5 and a 6 here. Okay? So there's only 2 ways to show this. So I'll use my systematic chart to help me figure out the number of pips that could possibly be showing. Okay? That's one way of doing it. That's kind of making a chart. All right? We're developing strategies. So we're using this table mentality to figure out, find the sample space, possible outcomes of all the different 2-digit numbers that can be made with 1, 3, and 8. Let's make a table. 1, 3, 8, 1, 3, 8. Do you see how this is a lot like that last problem that we did? Instead of having 6 sides to choose from, we only have 3 possibilities to choose from. And so when I draw this out, in this first box here, I'm going to have 11 because it's a 2-digit number. I use 1 from this column, 1 from this column. This is going to be 31. This will be 81. This is going to be 1, 3. This is going to be 1, 8. This is going to be 3, 3. This is going to be 8, 3. This is going to be 3, 8. This is going to be 8, 8. So how many possibilities are there? 9 possibilities. And what are they? Here they are. 11, 31, 81, 13, 33, 83, 18, 38, 88. This is my sample space. Okay? My sample space is the list of all the outcomes. Okay? So that's how I do that with a chart. Another way to do this is to use a tree diagram. Okay? This would be like what we would do if I was saying I have 3 neckties, I have 2 shirts, and I have 2 pairs of pants. How many possible outfits can I make? This is what we're doing right here. Okay? And so let's look at exactly how this works. If I'm saying I have choices to begin with, I have 2 possible CPUs. And so that's going to be C1 and C2 because I have a possibility here of, from C1, how many possible hard drives could I match it with? 3. And so this is going to be H1, H2, H3. But also C2 I could match with H1, H2, and H3. I'm out of space. Okay? Then from there, we have another step because we have 2 possible monitors. So I'm taking computer 1, or CPU 1, matching it with one of the 3 possible hard drives. Well, then I have M1, M2 off of each of these. I'm exhausting the possibilities. Okay? So how many possible computers could I make? I could make C1 with H1 with M1, that's a comma. Or I could make C1 with H1 with M2, etc., etc. You see how this works. And so down here I have to do the same thing. M1, M2, M1, M2, M1, M2. Okay? This is a very simple example. But look how complicated it gets. How many possibles do I have? I have 6, 12. 12 possible. 12 possible computers. That's with 3, 2, and 2 possibilities. What if I had 10 pairs of pants and 15 shirts and 30 neckties? You see how intricate and difficult this would get very quickly. Okay? So is this method efficient? No, it's not very efficient. But what we can do is we can help ourselves by finding out a different way to do this. How so? Let's take a look. Let's use horse racing as an example. The trifecta is choosing the order of the first 3 horses in a horse race. Okay? If there are 8 horses, how many possible orders are there for the first 3 horses? Consider each spot individually. First, second, and third place. At the start of the race, before anyone has crossed the finish line, how many possibilities are there for first place? 8. Anyone could win. We don't know who it is. It could be any one of those 8 horses. Let's think for a minute. If we take the possibility that the first horse crosses the finish line, first place is out of the running, there's no more possibility for first place. How many horses could possibly win second place when that horse is done? Well, only 7 could be left for second place. Because after the first horse finishes, there's only 7 horses left. Well, when 1 horse crosses for first place, 1 horse crosses for second place, how many horses are there remaining to be in third place? There's only 6 left. Okay? And so the way to find out the number of possibilities is to say 8 times 7 times 6. Because that is going to give us the number of possible outcomes for the first 3 horses. That's going to be 336 possible outcomes. Notice, I didn't make a tree. I could have. I didn't make a chart. Could have. I didn't draw a diagram. I just simply said, what is the math behind this? Let's think logically. Think about the math. Okay? This is the counting principle. The counting principle just says we're going to use the number of possibilities to figure out the places. Okay? So, try this one on your own. This is example 6. This is the medal stand. There's 9 runners this time. 9 runners. Still a race. How many possible orders are there for the gold, silver, and bronze medals? Pause right here. Try this one on your own. I'm going to keep rolling through it. Once again, I'm thinking gold. I'm thinking silver. I'm thinking bronze. In the first box, on the first medal stand, there's 9 possibilities. So when one person finishes, there's only 8 left. When the next person finishes, there's only 7 left. Okay? And so when we figure out what this is, let me grab my calculator. 9 times 8 times 7. That's how it works. 504 possible outcomes. Okay, guys? So that's the counting principle in a nutshell. A couple more things. Counting with and without replacement. Because that was without replacement. We're saying one person finished, they couldn't come in second place also. But what if we had like a box full of rubber, like racket balls or something, or bouncy balls? Okay? So what we've got here is a blue, a green, and an orange, and a red. And if I pull one out at random, I just pick the orange one just because. Assuming that the ball is replaced each time, how many possible outcomes are there for pulling 3 of them? So my first one was orange, okay? And so if I pick it random again, and I pick the green one out this time, and I put that one back in, and I randomly pulled the orange one again. We want to figure out how many possibilities there are because, see, this isn't like that problem where they finished in the horse race because orange could be picked again. Orange could get into that 3rd slot, or I could pick all orange. Okay? And so this is with replacement. And so what we need to understand is repeats being allowed, repeats not being allowed. How many 4-digit numbers can be formed with these numbers, assuming that repeats are not allowed? Well, let's look at how this works. Okay? So if we say that there's 9 possibilities for the first, slot there. Okay, 9 possibilities for the first slot. And so what we are going to do is we're going to consider the fact that now there's only 8 possibilities left. So we're going to have 9 times 8 times 7 times 6. Okay, and so what we're left with is 3,024 possible numbers, i.e. 9,567. Okay, you couldn't have 9999 because there's no replacement. There's no repeats allowed. Okay, so for example, that's one of them. So there's 3,024 possible numbers. Let's look at that if there were repeats allowed. So for example, if I choose 9, but then I chose 9 again, then I chose 9 again, then I chose 9 again, this would be allowed. Well, let's think about this in terms of those boxes once again. Okay? And I'm going to be multiplying those boxes together. And in the first slot, the first number of that number that I'm making out of 4 digits, I have 9 possibilities. Well, in the second possibility, if I can pick that same number again, I have 9 possibilities again. But then I have 9 possibilities again, and I have 9 possibilities again. You see how huge this can get. Okay? And so if I multiply this out, 9 times 9 times 9 times 9. 6,561 possibilities. That's a lot of possibilities, guys. If we had tried to write all of them out, we'd be writing for a month. Okay? You don't want to write that much. So learn how to use this counting principle with and without replacement. Okay? And so these are for you. Okay? Try these on your own. If we have 5 letters here, okay? If we can replace, I'm talking words, I'm talking like sets of 4 letters, i.e. we have 4 boxes here. Okay? These words are actually just sets of 4 letters. Okay? So think about it in terms of that race mentality where we have 4 boxes. If I can replace, how many possibilities do I have? If I don't have replacement, how many possibilities do I have? Okay? Pause. See if you can do this one on your own. I'm going to roll through it here. If I can replace, I have 5. I have 5, I have 5, I have 5. So I can multiply all those. So I've got 5 times 5 times 5 times 5. $625 possible. But if I can't replace, I still have those same 4 boxes, but I only have 5 possibilities. Then I only have 4 left. Then I only have 3 left because I've already chosen a couple of them, times 2. So I've got 20 times 3, which is 60, times 2 is 120 possible. Okay? That's how this works. It's actually a fairly simple concept to kind of grasp once you get it. Okay? Try this. Try to see if you can do this one on your own. We'll leave this one for you. If you want to write about it in the summary of this video, go ahead. We'll see you tomorrow in class. Thanks for watching, guys.